Hello everybody, this is lecture 2.1, Systems of Linear Equation and Elimination. This method we'll learn here, how to solve systems of equations, is going to be used many times in this course. So you'll get used to it eventually. We'll do some practice in this lecture, but as we move on from this section and from this chapter, we will continue to use these methods of solving systems of equations. So let's start talking about what a linear equation is. Okay, so a linear equation, it depends on the on the number of variables. Let's see where I was. Back at the top here. Good. So we have a system of equations, or a linear equation in n variables. So here we are. And the variables will denote by x1 to xn, although there's many different choices of labels for variables. So let's, most of the time we'll stick to this, and the textbook sticks to this, the x's being the variables. But as you move into different textbooks or different applications or outside this course, they may choose different letters. So you'll have to be aware of what symbols they're using for the variables. But a linear equation looks like this. Once you've identified the variables, it has this form where you see there's numbers A1, A2, etc. to B. These are numbers, constants we'll call them. And they're multiplying on the left. The A's are multiplying the variables, so we call them coefficients of the variables. And on the right-hand side is just a single number by itself. If the right-hand side happens to be 0, b equals 0, then we call it a homogeneous linear system, and we'll talk about those later on. They'll have a special role for us. Okay, so some examples, just to get used to this. Using the variables x1, x2, x3, let's write one down this way. x2 plus x3 equals 7. Now notice in the expression here that we're given, it's quite ordered. You start on the left with x1, and then the next term in the equation has an x2 in it, etc., until you get to the last variable with xn, and then the right-hand side. But it doesn't always have to be given that way to you. So for example, I'll choose a linear equation where my variables are called z. So there's z3, and then my coefficient being numbers. I'll use pi for this one, coefficient in front of z1, and then minus 3z2 plus 4 equals 0. Okay, so I purposely wrote this in a less orderly fashion because that's maybe the way the equation is given to you. So I didn't order the variables from left to right, and I didn't put all the constants on the right-hand side, but you can do that afterwards. We would like to have our equations, and as we'll see below, our systems of equations in an ordered form as presented in these notes. So that may be something you'd have to do at the beginning. Let me give you another example. So my variables are now y's in this equation. So 6y2 plus 4y3 plus 1 equals 3y1 minus 2y2 plus 4. Okay, so this is not given in an orderly fashion. So let's rewrite it then. This one right here, just to put it in an orderly fashion. So I'm going to rewrite it so that I have all the y's grouped together, all the y variables grouped together, and I'll put the right-hand side, all the constants onto the right-hand side. So when I do that, I'll have 3y1, and then I'll group the y2's together, and then I'll get minus 8y2. And then I'll group the y3's together, move them over to the right-hand side. That means gives me 4y3. And then I'll put all the constants on the other side of this equation, which makes it minus 3. Okay, so I did some minor manipulation of this equation, moving terms around, grouping terms, just to put it in a more orderly fashion. Okay, so that's something you may have to do in this course or outside this course when you're faced with linear equations, because we're going to introduce a technique in this section for solving equations, and they will need to be initially put into this ordered form. Okay, so it's worthwhile to get used to that. Before we move on, let me give you an example that's not a linear equation. Actually, a couple examples. Linear equations are quite special in that they're pretty simple. If you think of it from the point of view of calculus, you almost hardly ever deal with them. But let me give you some examples of equations that are not linear. So we would say they're nonlinear. Nonlinear meaning not linear. So here's an equation in the variables x1, x2, x3 that's not linear, and that's because of this term right here, okay? So when we say to check whether an equation is linear or not, you go to this definition up here, okay? So in English, if you want to explain that in English, it says that on the left-hand side, the variables are only multiplied by coefficients, by constants, a's. They're not multiplying themselves against each other, or they're not multiplying themselves together to get powers of 2 or powers of 3. And also, you don't get functions that are not linear appearing in these equations. So for the second example, also in the variables x1 and x2, say, I would write, say, 3 cosine of 2 times x1 plus 2x2 equals 7. Okay, so the term that's causing trouble here, that's making it nonlinear, is this cosine of 2x1. So this is not of the form given above. So it's not simply something times x1. It's actually in the argument of a function that is not just a constant multiplying x1. Okay, so these are two examples of non-linear equations, and that is not the subject of this course. This is, you might find things like this in your calculus courses. Okay, so in that sense, because you're not dealing with terms like this, linear equations are rather simple. Okay, but what makes it difficult for us is that there could be many variables in them, and also we're going to be talking about solving systems of equations, and that we'll get into that a little bit later on. Okay, so they're actually quite a complex problem to deal with. All right, so what do they look like geometrically? Well, you know, you might ask, well, what are we trying to do? Look at an equation geometrically. We're going to make some interpretation of what this equation means. So in R, which means you have one variable, I could have a linear equation could look like this. So here's an example of a linear equation in one variable, right? X is the variable. It's multiplied by a constant, and it's put in an orderly way. I put all the constants on the right and the variable on the left. Now you recognize this equation. What we're interested in, as we'll talk about in this section, is the solution. And you can see what the solution is. X equals minus 2/3. All right, so when we say what does it look like geometrically, we mean that, what does the solution look like? So solutions. Okay, so I see the solution here. If I drew it on the number line, so there's 1 and there's minus 1. So this is R, this line. Then I can see this equation, its solution is right here. Okay, so it's just a point on the line. Okay, now in R2 means we have two variables now. Let me call them x1 and x2. So for example, a linear equation in two variables is this. That's one example. Now, if I draw my x1 and x2 axes, in R2. Okay, so now we're in R2, and we ask what points in R2 satisfy this equation, and we recognize that as a line. If I drew all the points that satisfied that equation, then I would get a line. So let's sketch this line. So I'll just put down a few fiducial marks here. So there's 1 and there's 1. And what I'll do is I'll just plot the x1 and x2 intercept. So the x1 intercept is this point 1. Maybe I'll put it in blue. There it is there. And the x2 intercept is 1/2. Okay, so it's here. Okay, so I'll draw a line through that, and this will be what we mean when we say, what does a linear equation look like in R2? We mean the solution. And now it's not a single point, so I'm going to use the terminology that we will introduce later on. The solution set is that line. Okay, in R2. And in R3, we mean a linear equation in 3 variables. So let's just write one down. 2x1 plus x2 minus 3x3. And if you were listening to my previous lecture, you'd say, or the previous lectures, we'd recognize that as the scalar equation of a plane. Okay, scalar equation of a plane. And as I described in the previous lecture, we use this form of equation describing a plane to discern whether a point in R3 lies on the plane or not. If we take a point in R3 with coordinates x1, x2, x3, I can decide whether it's on this plane or not by substituting in its coordinates into this equation and seeing if it holds true. Okay, so so this gives us a plane. So the answer to the statement at the top here, what does a linear equation in R3 look like? The solution set, okay, the equation, the plane is the solution set. Okay, so it's the set of all points, that is, points with coordinates x1, x2, x3 that satisfy this equation. So the solution set is a plane. And just for reference, we can recognize that this plane has the normal 2, 1, minus 3. So you could make a sketch of this. I won't make a sketch of this. There's plenty of sketches in the textbook. Okay, so there's a geometric interpretation of these linear equations in the sense of their solutions. Okay, so as I mentioned above, one reason why linear equations can become complicated is there could be many variables. So you can see how this is going to proceed in R4, etc. In R4, hopefully you'll remember that from last lecture, a single linear equation is the scalar equation for a hyperplane. Okay, I'll just write that down. Actually, for Rn, maybe I'll just take that out. So a single equation in Rn is the scalar equation of a hyperplane. Okay, now I can't really draw those, but that's what we talked about in the last lecture. All right. So I can have many variables in the linear equation, but what often happens is that we have systems of linear equations. Okay, so that's a more complex situation, and this is probably an aspect of this course which is diverging from your calculus course. Certainly you've seen linear equations in calculus, and you didn't pay much attention to them because they weren't that difficult to deal with. You're mostly dealing with nonlinear equations there. But you rarely dealt with systems of equations. So we're going to talk about that, and that's going to be a main theme in this whole course, is systems of linear equations. So what we mean by a system of linear equations is a collection of linear equations, all of them in the same set of unknowns. All right, so my unknowns in this description right here will be x1 to xn. So every linear equation I discuss in this system of linear equations will be an equation in these variables. And here they are here. And now what I have are m of these equations. Okay, so you see that in this direction there's m equations. So that's the first one, that's the second one, that's the mth one. And you can see how I'm counting these equations by the particular indices here. It's the first component of these variables there. Okay, so 1, 2, down to m, and they all have that same pattern. It's going to be important for us to write our equations in a particular form because we're going to do some manipulations on them. So this labeling, these subindices, the first variable is listing the equation number or the rows here. And you can see them again over here, B1 to Bm. And then the second variable index for these variables, A, is labeling the variable that it's associated with. So A11 is a variable, associated with the variable x1, a12 with the variable x2, and they end at a1n when you get to the nth variable. So along this direction here, we have n terms. Okay, so n this way and m up and down vertically, m rows and n columns. Okay, so this is a nice orderly way to express a system of m equations and n unknowns, and this will be typically how we will use equations when we're faced with them. But once again, in applications, you may not be given the system in this nice form, and you would have to put it into this nice form to apply the methods we're going to learn in this section. So here's an example of a system of 3 equations in 4 unknowns. Okay, so I'm going to call the unknowns x1 again. So I'll write down my first of 3 equations, and each one of them I'm going to write in this orderly way, which again may not be the way you first encounter them, so you would arrange them as I did on the previous page. So you can see I'm already pacing myself across from left to right. I left a gap there for my x3, so it happens not to be appearing in this equation. You can think of that meaning the coefficient in front of x3 is 0 here, so we don't typically write 0 times x3 when we don't see that variable, we just leave it out. That's my first equation. Now I'll move on to my second equation, and I'm going to order it in the way that you see above. So I'm going to start with x1 on the left and move across. The second equation doesn't have an x2 term, so I'm going to skip over to the x3 term, which does appear in it. So there it is. And it has an x4 term, and it has a 3 on the right-hand side. So once again, it's an orderly equation. And then my last equation doesn't have an x1 in it, but it has an x2 in it. And then an x3 minus 4x3 and a plus 3x4, and then the right hand side in this case is 0. Okay, so that's an example of a system of 3 equations in 4 unknowns and written in a nice orderly fashion. All right, now we can now talk about solutions of systems in the case of the linear equation in 2 variables, and I'll just go back up to here to point out what we mean. So remember in R2, when we talk about a linear equation in R2, we're interested in the solution set, and we know that the solution set will be a line, and we can sketch that line. So there's, in this particular case, I should write it down here, there's infinitely many solutions, because there's infinitely many points on that line. And actually, let me write up here, this one is the unique solution, has a unique solution. All right. And in R3, this plane also is infinitely many solutions. I should write this down because it is going to be an issue for us to discern whether an equation or system of equations has many solutions or not. They don't have to have any solutions, as we'll see below, systems of equations, as we'll see below. So going back to the 2 variable case, so its solution set is a line. So now we're looking at a system, though, of equations in 2 variables. So 2 equations in 2 variables. Okay, let's call the variables x and y. So there it is right there, the two equations. Now the coefficients are not specified, so we don't know what exactly these lines are, but I can draw possibilities. Okay, so let me draw one example here. So I'll draw my x and y axes. So x and y axes. And then I'll draw, hypothetically, what 2 lines may appear to be. So there might be one line like this. So let me label here that this first equation will correspond to my drawing of line 1, and the second equation will correspond to my drawing of line 2. And if I knew the A's, B's, and C's, I can actually sketch exactly what those lines are, but I don't know them, so I'm just going to sketch some possible situations. So let's call that one L1. Fine, and then L2 could look like something like that. Okay, that could be L2. All right. Now, when we're looking for the solution of a system, remember we want, well, not remember, but it's defined down here. I'll just preempt it. A solution of the system is a solution that satisfies all the equations simultaneously. All right, so here we're looking for pairs of numbers x, y that satisfy not only the first equation but also the second. If I just go back up to here for a second, see that for the solution set here, it's the pairs of numbers x1, x2 that satisfy this equation. There's many such pairs of numbers. When we get to a system of equations, though, we're looking for more than just the solution of a single equation. We want it also to be a solution of the next equation and all the equations in the system. So here there's two linear equations in two variables. So each one of them has a solution set that is a line, and I've drawn these two lines. But what we want is the solution for all equations. Okay, so simultaneous solution for both equations. Okay, and that's what we'll define just below as the solution to the system. So it's got to be a solution that's works for both equations. So in other words, looking at the first equation and its solution set, which is this line, we ask, are there any points in this line that also satisfy the second equation? And what that means geometrically is, are there any points on line 1 that also lie on line 2? Okay, and now you can see where they are, where it is actually, it's right here. Okay, so there, I just put a dot on it, is the solution set. Okay, set to the system. Right, there's only one now. A single linear equation in two variables has infinitely many solutions, but when we ask for the solution of two of them, it could be reduced to one. So that's one possible example. Okay, so in this case, this particular system of equations has just a single solution. But there's other possibilities, and I'll make some more sketches here. So there's, it depends on the orientation of these lines. So we could have now two lines like this, so two parallel lines. So this is my L1 and L2. Okay, so those could be the solution sets of those two equations. And I ask you once again, if we want, are there any solutions for the first equation that are also solutions for the second equation, which means geometrically, is there a point on L1 that's on L2? And there isn't any. So here we conclude that there's no solution. So now we're getting into a realm that doesn't appear usually in a single equation. When you start to write down systems of equations, it could very well be that there's no solution. So this is an example of no solution, two parallel lines. So whatever those two equations must look like to present lines like this, they would have no solution. So that's one possibility, no solution. And then we have a third possibility here. So there's my x and y axes. And I could draw maybe my line L1 here. Now, L2 will also be a line parallel to L1, but it's going to be on top of it. So, well, there you go. Right? So it's like the second example, except the line L2 actually sits on it. Okay, so this could very well happen. The equations don't have to look exactly the same, but you know one's going to be a multiple of the other. Nevertheless, we're just going to assume that we don't see it right off the bat. But this could also happen. Now in this situation here, if this is the case for this particular system of linear equations, we see that there's infinitely many solutions. Okay, so there's three different possibilities that can happen in this scenario of two equations in two variables. You may have a single unique solution, you may have no solution, you may have infinitely many. Notice you can't have a situation where you have exactly 2 or 3 or 4 solutions. That will never happen here because lines just don't intersect that way. It's a geometric fact. But we will prove that also algebraically. So now we preempted this definition of a solution set. Okay. So at the beginning we talked about a solution. I'll just remind you here. Or did we say that yet? So a solution would be for a single equation. Then I mentioned it in my discussion. You plug in the variables, it satisfies that single equation. But for a solution set, we mean more than that. So it's a set of numbers. So here they are, S1 to Sn, that when you substitute it in for the variables, so now the variables assume these particular numbers, all the equations become true. Okay, so what I was discussing up here in my examples is just single equations, and I was actually describing their solutions. Now we're talking about something more complicated. We're asking for solutions that satisfy all the equations, not just a single one. Okay, so that's what we, in this example 6, I was describing. So the solution set would be the collection of all these n tuples, in this case, S1 to Sn. There could be many of them, there could be none of them. There could be no such solutions, but we're looking for them, these n numbers that satisfy all these equations. And we'll write it out as in vector form, like this. So that would represent one particular solution in the solution set. So the set of all solutions would be what we call the solution set. So there'd be a collection of these n tuples, points in Rn, that would be the solution set. Okay, so we already saw one example up there, which was 2 equations and 2 unknowns. So now you have many variations on this theme. So let's take the example of 2 equations and 3 unknowns. Okay, so now we know that in this case here, the solution sets geometrically are planes. Okay, are the solution sets of each equation. Okay, so when we're asking for the solution set of the system, we're asking for points in the solution set of each equation that are also solutions of the other equation. So in other words, the points on the planes that are in both of these planes. So we're looking for, so the solution set will be the intersection of these planes. So solution set is the intersection of these planes. And I'll try to make a sketch here of these 2 planes. If I could sketch these or see them visually, then I would be able to discern what that solution set is. So let me just draw you a typical situation, and you can do this yourself. You know, 2 planes are like 2 sheets of paper. So just take 2 sheets of paper, sort of randomly oriented in space, and you'll see that what typically happens will be this. So there's one sheet like that, and then I'll draw another sheet kind of going like this. Okay, so that guy intersected it, and I have one sheet kind of more flat like that. Okay, so maybe you can try to visualize that. So what we see here, and I'll draw it with a blue line, is a line of intersection between these 2 planes. Okay, so there's the line of intersection of these 2 planes. And if you play around with your piece of paper, you'll see that typically this is what happens when you have 2 pieces of paper in R3. Where they intersect will be a line, and they'll typically intersect in this line. So this is the solution set, okay, in this particular situation. And we see that there's infinitely many solutions because there's infinitely many points on the line. So that's one possibility. I'm not saying this happens all the time, and we'll see some examples below. It's similar to this example, these examples of the lines. It depends on how these lines are oriented. So I took what is more typical. If you randomly just orient two planes, they'll intersect in a line. But you could have the case of no solution if planes are parallel and non-intersecting. Okay, so that's similar to the 2 lines above that are parallel and non-intersecting. Okay, so then you could have no solution, and you could have infinitely many solutions. In this case, if the planes are parallel, but they do contain a common point. So if planes are parallel and intersecting. So what I mean by that is that they have a common point, and if they have one common point, then they share all points together. So in this case, we see in the situation of 2 planes in 3 dimensions, we have the possibility of infinitely many solutions, this one here. We have the possibility of no solution if the planes are parallel, non-intersecting, or infinitely many solutions. I just point out here because I'm using a term here. Planes are parallel. Okay, so this has to do with the normal vectors. You can tell if two planes are parallel by looking at their normal vectors. Are they parallel? Okay, and two vectors are parallel if one's a scalar multiple of the other. Okay, so we can tell if we have the scalar equation of these planes, then it's easy to tell whether they're parallel or not. Whether they're intersecting or not, it depends on the, you need to look at the D on the right-hand side. All right. Now it's not just the D, it has to do with the also the way the normal is defined, but once you've decided whether the planes are parallel, you still have some more work to do to decide whether they're intersecting or not, and that has to do with the right-hand side of those equations. But you can do those things pretty simply. Okay, so this is a page, I think it's from the book, and it's nicely done, nicely drawn. Now we're talking about 3 equations in 3 variables. Maybe I should go up here and just add another situation here. Okay, so let's just do this one up here. 3 equations. What can possibly happen? 3 equations in 2 variables. Okay, I'm not going to write them down. I'm just going to write down what you may expect to happen. So there's my axes. So if I have 3 equations in 2 variables, I'm going to sketch the solution sets of each equation. That is 3 lines. And that might turn out to be something like this. Let me just make a little sketch here. So you could have one like that. So that could be the solution set of my first equation. That could be the solution set of my second equation. Okay, so that's typically what would happen if you just drew 2 lines. They'd be a single point. But now there's another equation. So now, without being very precise, I mean, if you put a blindfold on and just drew a line, it would probably do something like that. Okay, all right, so let's say that our 3 equations have these 3 solution sets, these 3 lines. So now we ask, what is the solution set of the system? Okay, so you think, well, I'm looking for points that satisfy all 3 equations algebraically. So geometrically, that means I'm looking for a point in R2 that sits on all 3 lines. Okay, now it's easy to find points that sit on 2 lines. I can see them. But there's no point that sits on 3 lines. Okay, so there's no solution here. And that's typically what's going to happen when you have 3 equations just sort of randomly written down, and these lines turn out to be kind of randomly distributed. You're not going to have any solutions. All right. So it happens very commonly that a system of equations won't have any solution. Okay. There is a case where 3 equations have a solution in 2 variables. This line L3, if I moved it down, and I'll just put that in some kind of light yellow color here, you know, if my L3 was here and it went through that point, so this is my new L3. If it went through that point, then this system would have one solution. It'd be that common point there where all 3 of them intersected. Okay, but the original blue ones, they didn't. Okay, so this is giving you some idea of the interplay between number of variables, which turns out to be the dimension in the space we're looking at the solution sets, and the number of equations. You know, there's a relationship between what to expect in the solution set, and we're going to do that down here now. So I talked about here two planes in 3 dimensions. Now they have some sketches of 3 planes in three variables. So there's many more possibilities here, and we can see what's going on. So what can happen in the first example here, I'll just put some blue on it. We have 3 planes that are parallel and not intersecting. So this means that the 3 normal vectors are parallel. Okay, so this is no solutions. We can have 2 of the planes parallel but the third plane not parallel, so it cuts through them. But notice there's no common intersection. Okay, there's no points that sit on all three planes, and same with this one here. So here, none of the planes are parallel, but three of them don't intersect in any common points. Here, the three are parallel and they're sitting on top of each other, so the whole plane is the solution set, so there's infinitely many solutions. Here we have two planes, say the bottom two. Let me give it a little note here. So this one here and this one here. So that's like the picture I drew up here, two planes intersecting in a line. So there's that line right here. And then the third plane is quite carefully put down on that line. So in this case, the case of three planes, three equations and three unknowns, we have infinitely many solutions. This is more, the next one is the more common situation where I don't choose the orientation of the planes carefully. So typically what happens, like up here for three planes, so for two planes they typically give you a line. Now if you add another plane, a plane will typically intersect a line in a single point, won't it? If you think about it. So that's sort of the typical situation, and that's what we see in this one right here, that the point which is right here is the solution set of the system. Okay, so that's what will typically happen if you want to look at it that way. Here we have all three planes are parallel, but two of them coincide, the third one doesn't, so no solution. And here we have the situation where two planes coincide and the third one is not parallel, so it does intersect in a line. Okay, so that's the solution set right here, this line. Okay, so we see some variety of possible solution sets, what to expect when we have three equations and three unknowns, because we can visualize planes in 3 dimensions and we can see the various possibilities. So now pay attention to the way we counted the solutions. We had, let me write it down here, a number of solutions in the set. Okay, we've seen examples of 0 solutions. We saw 1 solution, and we saw infinitely many. Okay, so notice 0, 1, infinity, as we saw above. So there's no way you're going to get a solution set that has exactly 2 points or 3 points or 7 or 24 points. It never happens. Here it's always 0, 1, or infinity for systems of equations. So there we go. That's actually a theorem. It's not proven right here, but we will find a way to prove that using our algebra that we're going to learn to solve these systems. Okay, so the proof here, there is a proof in the textbook. Okay, but we will be able to describe this theorem once we learn how to solve a system of equations, which is what we're getting into next. So first of all, some terminology, consistent and inconsistent. Okay, so consistent means that there's at least a solution, at least one, and inconsistent means no solutions. Okay, so we've seen examples of this happening. So no solution is synonymous with inconsistent. If there's at least one solution, which means there could be one or infinitely many, it's called consistent. Okay, so now our goal is to solve a system of equations. Okay, so we're solving systems of equations. Now notice this will also be applicable to a single equation, because a single equation is a kind of trivial system of equations with just one equation in it. Okay, so everything we talk about here also applies to that situation. So our task here is how to solve a system. To solve a system of equations, which means how do we find the solution set? Okay. Now, it's a formidable task, okay, to begin with, as we'll see in some of the examples here. Okay. So our strategy is to do the following, is to simplify them. Simplify them. Okay, now, we have to be careful what we mean by that. Simplify them. Okay, and this is what we're talking about in this section here. Okay, so I'm going to give you some motivation by looking at some examples. So first of all, we have, I'm going to go to the case where there's just a single equation. So let me look at one single equation, and let's just keep track of what we are doing when we say we solved it. And you've done this many times, many years ago, you started to look at these kinds of equations. We're going to use these methods here, A, B, and C, to simplify equations to the point where I can see what the solution is. Now this one is pretty simple. I can see what the solution is without doing anything else, but I'm still going to pretend I want to follow these rules. So I'm going to use rule 1, multiply one equation by non-scalar number. So I'm going to multiply this this single equation, multiply by 1/3, and it does simplify it in the sense that it looks like x equals minus 7/30. Okay, so this equation here is, I'd say, simpler than this one in the sense that it's obvious what the solution is. So this is what we mean by simplifying them, is it's easier to see what the solution set is, the simpler they get. Okay, so this is as simple as you can get, and it's obvious what the solution set is. Now I'm going to also introduce some terminology here that we'll use later. So this equation and this equation, okay, these are two different equations, but they have the same solution, so we call them equivalent equations. Okay, now this is defined in the text, so I'll just write out parenthetically what it means. They have the same solution set. Okay, so this definition, although the solution set, this is just the solution of this one single equation. So the fact that we introduced this term equivalent equations, meaning the same solution set, is hinting that what's important in a system of linear equations, or any system of equations, but let's just concentrate on linear equations, is not so much the form of the system, but it's the solution set. That's what's interesting to us. And now, as we'll see as we go through these examples, and as you work on your homework problems, you'll begin to realize that there's many ways to represent a solution set from a system of equations. That is, there's many systems of equations that look differently but have the same solution set. And what we're trying to do is manipulate the initial system of equations, simplifying them using these three methods, A, B, and C, so that we get a system of equations that is much simpler, and simpler to the point that we can now identify what the solution set is. So that's our goal here in this section. So I've used that one strategy here, the multiplying an equation by non-zero constant. Notice it's non-zero, and you can see why it can't be zero. If I multiplied an equation by 0, so if I multiplied this equation by 0, I just get 0 times x is equal to 0. What's the solution set of 0 times x equals 0? That is, what values of x satisfy that equation? Well, all values of x satisfy that equation. So when you multiply an equation by 0, you're drastically changing the solution set. Okay, so that's why we don't want to do that. But multiplying it by anything else is fine. It won't change the solution set. So number 2 is a single equation again. Let me write one down. 2x minus 1/2 y equals 5. Okay, so let's do some simple algebra to have an easier way to identify the solution set. So I'm going to first multiply by 1/2 because I want to isolate my x variable as my leading variable. So I'm using some terminology that we're going to use later on. So I want to use x as my leading variable, and I'm going to use y as a free variable, as it will describe later on. So if I multiply by 1/2, that gives me a 1 in front of the coefficient of x, and it changes my equation into this one, which is an equivalent equation. Okay, once again, equivalent means same solution set. So in other words, geometrically, remember that's a line. This is also a line. These are the same lines. Okay, so I haven't changed the solution set, but I've changed the equation. So I'm at this stage right here. And now what I'm going to do, just to express my solution more intelligibly, I'm going to solve for x. In other words, I put everything else on the other side. So x is equal to 5/2 plus 1/4 y. And the reason I do this is because now it's explicit that there's infinitely many solutions, and why there are infinitely many solutions. So here I don't have to draw the line to show you this, because we're not going to be in the position where we can draw solution sets of linear equations, because there are going to be many, many variables and I can't draw them. So I'm going to just do this algebraically. So algebraically, when I write the equation this way, where I've isolated the x on the left and I put the other variable on the right, I see right away that there's infinitely many solutions because there's one for each choice of y. Okay, so I've distinguished y here as my free variable choice of y. Okay, so I'm introducing some terminology that we're going to use below. That's my free variable. Okay, and my x is my leading variable. Okay, so free variable, it's a parameter, i.e. parameter. Okay, so it can be chosen freely. So let me write out some of the solutions in the solution set now. Solution set is curly bracket. So remember, solutions to this equation are going to be two tuples, so points in R2, so x, y coordinates. So what I do is I select values for y, and then I just compute the x from this equation here. Okay, so select y and then compute x. I can get all the solutions this way. So my first choice, why not choose y to be 0? Okay, so that gives me x is 5/2. And then I'll just work on, if I chose y to be 2, then I would get 5/2 plus a half, so I'd get 3 and 2, and then etc., etc. Okay, and now I can't write them all down, there's infinitely many, but at least there's an order about this. By choosing y, I get a new solution by changing y, and I just compute what the x has to be for it to satisfy the equation. Okay, so there's one example. Now I'll go on to a system of equations. Okay, so let's do a pretty simple one, two equations and two variables. So remember, geometrically, I'm thinking about the intersection of these two lines, but I'm working algebraically like we will do. Okay, so now I'm going to use this step C now, add a multiple of one equation to another. So what does that mean? So I'm going to use C. I'm going to write out what I'm going to do. I'm going to subtract. I'm going to subtract an equation, the first equation, okay, from the second. Okay. Now, before I write down what this means, this is a generalization of what you learned a long, long time ago. When you have an equation, you can add or subtract numbers on both sides and not change the equation. And that's what we mean. They're equivalent. You haven't changed the solution set if I add a constant, the same constant to both sides. But we're doing something more complex here. We're actually adding the same equation to both sides. Okay, so let me show you what we mean here. So new second equation. So I'm changing the second equation, and it looks like this. So I'm going to subtract the first equation from the second equation. Okay, so I have, there's the left-hand side of my second equation. Okay, so that's the second equation. And then on the, I'm going to subtract from it the left-hand side of the first equation. And I'll put it, so minus, and that's the x plus y. Okay, so that's now coming from the first equation. And now I do the same on the right-hand side. So I have my right-hand side of my second equation. There it is. And I subtract what's on the right-hand side of my first equation, which is, let me put it in blue, which is 1. Okay, so this is what we mean by subtracting or adding a multiple of one equation to another. And you see why this is an equivalent equation, because I've added the same quantity to both sides, equivalent. Okay, I've added the same quantity on both sides, namely x plus y. So I can think of x plus y or as 1. When I'm looking at the left-hand side of equation 2, I think of it as x plus y. When I look at the right-hand side of equation 2, I think of it as 1. So I've added the same quantity, or rather in this case, I've subtracted the same quantity from both sides of equation 2. When I do that, I get something a little bit more simple. So what does it look like now? So once I've done that, I get x plus y. So I haven't changed the first equation. I've just changed the second equation. So now just do the algebra right here. Okay, so x minus x. So I've eliminated a variable x, and I picked up another negative y. So I get minus 2y equals 1. So what we've done here is we eliminated, and this is a key process we're following here, eliminated variable x from the second equation. Okay, but I did it in a proper way that I wouldn't affect the solution set of the system. So I added the same quantity to both sides of equation 2, and that quantity was the equation 1. So you see, as I eliminate variables, and I'll just put that in yellow, this is our process of simplifying. All right. So you've probably been doing this already because you've been solving some systems of equations before, and you probably, that was your goal, was just to eliminate variables, as many as you can, and then see what you end up with. So we're doing that same process here. Okay, so I'm simplifying. So let me finish this one up. So now let's continue to simplify. So now I want to get to that stage where I want to identify leading variables and free variables. What variables depend on the other ones, and how many solutions do I get out of it? So let's continue on. So let me simplify the second equation. Now this kind of simplification is just changing the coefficients in front of the variables to be 1. It's just simpler to work algebraically. So let me just change that second equation. Let me multiply it by minus 2. All right. So this was step A now. Okay, so I'm using step A. So multiply equation 2 by minus 1/2. All right, so I did that. And now I'm going to do the same step A here, because now I can eliminate variable y in the first equation. So let's do that. Okay, so I'm going to do, let me write it out first. C, I'm going to subtract. As you'll see in this example, and as you'll probably soon learn in your homework, that this step C, where you're adding or subtracting multiples of equations to another, is the key step that really does the simplification. This is the one that eliminates the variables. Okay, so this is the one you will often be using. Here I'm going to subtract the second equation from the first. Okay. And once again, this doesn't change the solution set. Okay, so what happens when I do that? So my second equation is the same, so I'll write it first. So now I'm going to subtract y from the left-hand side of the first equation. I'm going to subtract minus 1/2 from the right-hand side of the first equation. So what I end up with is x, no more y, but my right-hand side changes to 3/2. So voila. That is an equivalent system to the first one. Okay, in that it has the same solution set. Now compare that to what we started with. So there's what we started with up here, this one here. Okay, now it's not obvious just by looking at that what the solution set is, or whether there is any solutions to the system. Remember, there doesn't have to be any. But if you are given that as your system of equations, well, you don't have to do any work at all. You see what the solution is. So this is as simple as it gets. The simplest form of a system of linear equations is when the solution is explicitly given to you. All right, and that's what we're aiming for when we do this process of manipulating systems of equations through these rules that were listed above. We're trying to get them into a form where we can see what the solution is. So now, finally, I see that there's a unique solution. And there it is. And let me write it out. It's going to be 3/2 and -1/2. And you can go back to the beginning and plug that in and see that that works, right? So x plus y is equal to 1, and x minus y is equal to 2. So it is a solution to the first equation. And there's no more solutions, because this equivalent system at the end here tells us that there's no more solutions. It's just this one. Okay, so that's a little hint of how we're going to do this. Now, things get pretty complicated in this course, because we're going to have many variables and many equations. And as you may have noticed in math courses, mathematics in general, notation is helpful. Notation helps us deal with complicated situations. So we're going to take a little detour into some notational terminology that will help us, assist us in keeping track of our systems of equations as we change them. Okay, so we're going to introduce the term matrix in this context. We'll talk about matrices a lot in this course, but here we're just using them as a kind of a notational convenience for systems of equations. So we have a system of equations right here, so m equations and n unknowns. Now, if you go back up here and take a look at what we did to simplify this last example, all I needed to know was what are the coefficients in front of the variables at the beginning. And I just used that and the right-hand side. So that's the, I'll just put a little dot in yellow. I mean, these numbers that are multiplying the variables. So there's a 1, 1 and a -1 there, and then the right-hand side, a 1 and a 2. Okay, so those 6 numbers, so in the first equation I see a 1 in front of the x, a 1 in front of the y, a 1 on the right hand side. In the second equation I see a 1 in front of the x, a -1 in front of the y, and a 2 on the right hand side. It's only those numbers that I needed to decide how to do the manipulation. Okay, I don't need to see the x's and y's, but I do need to know from those 6 numbers what variable they're associated to and whether or not they're on the right hand side. So once I put my system into this form right here, so that's my orderly form, okay, so x1 on the left, working your way to xn, all the constants on the right hand side, then if they're all in that form, then I can just eliminate my variables and not write them out. And I don't even need to see the plus signs either. All I need to know is those numbers. So that's the augmented matrix, and that's what's illustrated here. So I'll just write over top of the columns. You see these columns of numbers, the A11, A21, etc. Those are the coefficients of my x1 variable. And the next column over is the numbers A12 followed by A22, etc. Those are the coefficients of x2 in my system. And as I get to the end, I see my coefficients of xn, and then I see the right-hand side. Okay, so as long as we know the order that the original system was, then I only need to know these numbers, okay, to do my manipulations to simplify the equations. Okay, so I don't have to write down the variables or the plus signs or the equality signs. I don't need that when I'm doing my calculations, my simplifications. Okay, so we will do that, and that's called the augmented matrix for the linear system. So you can go, I wrote this arrow from system to augmented matrix. You can also go from augmented matrix to a system. So you can go back and forth, and we will go back and forth. And I'll do that as I go along here. So let's just practice writing out the augmented system. So there's my system of equations. It's 2 variables, it's 4 variables and 2 equations. So it's going to be a matrix that is wide but not very high, so it only has 2 rows. In the first row I see the coefficients in front of my x1 variable, so there's a 1 and there's a 2, and then the second column are the coefficients in front of my x2, and then x3, and then x4, and then the right hand side. Okay, and that's an augmented system. What we also should write down here, because it is in the text and it is something we will use, is the coefficient matrix, which, as the name suggests, is just the coefficients in front of the variable. So in this case, it's just everything but the last column. This is also very useful to us. this coefficient matrix. So it's smaller than the augmented matrix. You just drop off the right-hand side. Of course, when you do that, the coefficient matrix is not enough for us to determine the solution set. I need to know the right-hand side. But many operations that we will do on a system and later on in this course will be focused on the coefficient matrix. So it's good to introduce that right now, and it is introduced in the book. So that's the coefficient matrix. I know that in some, I'll put it up here, in some books and maybe in engineering texts and such, they might do something like this for the augmented matrix, just to emphasize that it is the augmented matrix and not the coefficient matrix, because it makes a world of difference if you're looking at an augmented matrix or coefficient matrix. So they may put a line right here, either dotted or solid, to distinguish the last column as being the right-hand side. So this could be what you might see in other textbooks with this dotted line. Then they don't have to say that this is the augmented matrix. Okay, that's not what we're doing here. We'll have either just a matrix that looks like this. So someone will have to tell you, are you looking at the coefficient matrix or the augmented matrix? So pay attention to the context of the place where you see this matrix. For example, if I mistook this to be an augmented matrix, you see how vastly different it is from this system. Okay, so on the right, this one here, if I interpret that as an augmented matrix and I only see 3 variables and two equations, okay, that's a different situation than what I started with over here, which was 4 variables and 2 equations. Okay, so it makes a world of difference if you make a mistake like that. Okay. Here we will just specify it in English. So moving right along, what we discussed above were these operations, and now we're going to translate those operations into operations on the matrix. So these are operations on the equations, which I used above, and this is going to be the operations on the augmented matrix. Okay, so how do those translate to operations on the augmented matrix? Okay, so when I multiply, for example, when I multiply an equation by scalar, I mean I'm multiplying that row in the augmented matrix by scalar. If I interchange two equations, I'm interchanging 2 rows in the augmented matrix. When I add a multiple of one equation to another, I'm adding a multiple of one row to another. Okay, so that's what it looks like when you're dealing with the augmented matrix. So let's do an example where we simplify a system of equations by applying these elementary row operations, those 3 that we listed there, A, B, and C. Let's do that here for this system of 2 equations and 2 unknowns. So we begin with the augmented matrix, so 2, 1, minus 3, minus 1, 1, 3. Okay. Now I'm going to use the symbol they have in the book, this wavy symbol, like a similarity, to denote equivalent systems. Okay, so this is what they use in the book, and it's customary. So this means it's an equivalent system. I haven't written it down yet, but I will. Equivalent system, equivalent augmented matrix. The first thing I'm going to do is, because I like to have, and this is what we will aim for, okay? I want to have a coefficient of 1 in front of my my variables, as many as I can. So I'm going to utilize the fact that there's already a 1 in front of the x in the second equation. So I'm going to change the second equation into my first. So I'm just going to interchange. So this is an example where you might want to interchange 2 equations. So there we go. So I'm there. Now I'm going to do something more serious. Okay, so this is equivalent to, so now I want to eliminate variables. So the variable I want to eliminate is this one here in the second equation. So I have a 2x in the second equation. I want to use the first equation to eliminate that 2x in the second equation. So what I'll do here is I will, maybe I should write it on the side here because I want to explain what I'm doing. So I'll just write it over here. I'm going to, let me write it in English in detail. So the new, maybe I won't use that color here. I want to use this. So the new row 2 equals, okay, I'm going to write out in English what operation it is. I did row 2 minus 2 times row 1. Okay, so in other words, I subtracted 2 times the first equation from the second equation. Okay, maybe I'll write that down here too, just to make sure you know what I'm doing. So I subtract 2 times first equation from the second. Okay, so in terms of the augmented matrix, it means I've subtracted 2 times the first row from the second. Okay, so that's what I'm going to do to eliminate a variable. So now I get the equivalent system. So for the matrix, I think about, maybe I'll do it in yellow just very faintly, and you might want to do this yourself when you begin. I want to subtract 2 times the first row from the second. So why don't I write just slightly above it what 2 times the first row looks like. You see that? So I get 2 minus 2 and 6. This is just in my mind's eye. Okay. So now it just allows me to be more cautious, more careful with my algebra. So now I'm simply going to eliminate or subtract that new first row on the top there in yellow, 2 minus 2 and 6 from the second row. But it's just in my mind's eye, so I'm not changing the first row. So the second row now becomes, so this 2 minus the 2 I see above there. Now I get minus 3 minus my minus 2, which gives me a minus 1. And I see a 1 minus a 6, which gives me a minus 5. Okay, so there we are. Now maybe I'll do it here just to show you what this system of equations looks like. Now my system of equations looks the following. It's x minus y equals 3. And now I have minus y equals minus 5. Okay, so if I were writing down the system of equations and doing these operations, this is the stage I'd be at. Okay, that's the augmented matrix of that system. But I'm not going to do that. I'm just going to work with the augmented matrix. I won't write out the system until I get to the very end. So I'm not done simplifying. So I'm here. Now, once again, I'll do something simple. I'm targeting now the y, the coefficient in front of y in the second equation. I prefer to have that to be a 1. Okay, it's just simpler for me to have coefficients of 1 in front of as many variables as I can, and we'll see how this assists us. So let me do that. So I'm going to multiply the second equation by minus 1. So I'll just write that down. Multiply row 2. When I say the second equation in terms of the augmented matrix, it's the second row. Multiply row 2 by minus 1. So that changes it to this one, 0, 1, 5. All right. And now I'm in the position to eliminate this y variable in my first equation. You see that? So you see what I'm going to do. I'm going to add, I'll just write it this way, add row 2 to row 1. So in terms of equations, it means I'm going to add the second equation to the first equation. When I do that, I get, so my second equation, my second row is not changing, but my first one does change. So here, the second equation doesn't have an x in it, so it's not going to affect what the coefficient of x is in my first equation. But when I add the second equation to the first, I'm adding a y to the minus y in the first equation, so that gives me a 0. And the right-hand side of the first equation, I'm adding 5 to it, so I get 8. Okay. Now this is pretty simple equation, or augmented matrix. So this corresponds to the system now. Let's write it out. X equals 8, y equals 5. Okay, so that's how far I've simplified my system to here. And I'll stop here because this is simple enough for me to read off the solution set. Okay, so you can check the answer, and I suspect you do this yourself, and I'll do it here too. So check, is this the unique solution to the original equation? So I'm going to plug it into the first system that I have at the top there. So for x I put 8, and for y I put 5. Okay, so I've done that the left-hand side of my first equation. So what I get 16 minus 15. Okay, and that's equal to 1, which is the right-hand side. So that solution, x equals 8, y equals 5, is a solution to the first equation. But I'm claiming this is the solution to the system, so I have to check the second equation. So I get, for x, I get 8 minus y, which is 5, and that is 3, and that satisfies the second equation. So this solution in terms of the two-tuple is 8, 5. Okay, that's the unique solution, obtained by applying the row operations to this system via the augmented matrix. Okay, pretty simple example. Things won't be that simple all the time, but you'll learn how to do this pretty efficiently, I'm sure. Okay, so this is it now. What we're trying to do is simplify our system of equations, and in terms of the matrix, we're simplifying this augmented matrix, and the form we're aiming for is called the row echelon form. Okay, so basically we aim for an augmented matrix of this form. Okay, so 1's up here and then 0's everywhere else, which means I've eliminated that variable from all the equations. And then in my next equation, I have a 1 in the second variable, but 0's everywhere else, above and below. Okay, etc., etc. So this is what we're trying to aim for, which is an elimination of variables. So in other words, I want to make many, many zeros in my augmented matrix, which corresponds to eliminating variables in the equations to the point where I reach a stage where I can at least identify what the solution set is. Okay, so that's our goal, and that's the simplest form we aim for, or almost the simplest form, is called the row echelon form. So this is the definition of this aim. Each row has is either all zeros, or the first entry you encounter moving from left to right is a 1, and that's what we call the leading one. Okay, so the first first non-zero entry. So what that means is from left to right. Okay, as you go across the row, left to right, the first non-zero term you encounter is a 1. We put all the zeros rows at the bottom. So some rows may turn out to be entirely 0, as we'll see. We'll put them at the bottom. And now for some orderly helpfulness to express our solutions more efficiently, we want the ones, the leading ones, to move to the right as we go down the rows, okay, like I sketched here at my aim. So in successive rows, as I go down, the leading one in the row lower is further to the right than the leading ones above. Okay, so I'm kind of get this diagonal one pattern here. All right, so that's where we're aiming for. So let's just look at some examples of matrices to identify whether they're in echelon form or not. Here it says we should circle the leading ones. Okay, so remember the leading ones, and I will circle them. Those are the first entries you encounter as you go from left to right. So I've circled them. Now I'm going to say whether they're echelon form or not. And here it's not, simply because these rows are in the wrong order. Okay, so this is the C, right? So the leading one in the third row should be further to the right than the leading one in the second row. So if I interchange those two rows, then it would be in echelon form. The next one, I'll circle the leading ones, and this one is in echelon form. So you see the first entry is a leading one, and the leading ones move to the right as I move down the matrix. Okay, let's continue on. So 1, 1, 1. So here we also have a echelon form. Okay, so notice the last column does not contain a leading one. Every row here did contain a leading one. Here's another example that is in echelon form. There's my leading ones. Here's another example that's in echelon form. Now this is not in echelon, sorry, is not in echelon form because the 0 row is not at the bottom. Okay, there you go. So if I interchange those two rows, then it would be in echelon form. Here, that's a leading one, that's also a leading one, and that's a leading one. So this one down here makes it not in echelon form. Okay, so that one shouldn't be there. Okay, so you can do some row operations to eliminate that one down there, and that's what we would do. So all these ones that aren't in echelon form, you can apply one of those row operations, those 3 row operations, to put it into echelon form. Okay, so these are not done yet. using those row operations. So let's move on to this one, this one. So there's my three leading ones, and that looks like it's echelon form. And this one and this one. There's my three leading ones. This one and this one too here. They both have 0 rows, so there they are at the bottom. So this is also an echelon form. There's my leading one. There's my leading one. Now this guy's a problem. That should be a 1. So it's not in echelon form because it's not a 1. But that could be easily changed. I would multiply the third row by 1/4, and then it would be in echelon form. Okay, so some examples. So solving systems in echelon form. So remember, we can move back and forth between augmented matrix and systems. As long as we know we're working with an augmented matrix, then I can translate it back into a system. So there's an example of a row echelon form, reduced row echelon form. So my leading ones, and they're moving from left to right. Let's write out what this system is. So we claim that when an augmented matrix is in reduced row echelon form, then the associated system of equations, it's possible to see what the solution set is when it's in that form. So let's write out the system of equations here. So I'm calling my variables x, y, and z. I see there's 3 variables. So x, for the first row there, x is equal to 5. And then I see y is equal to -2. And now I see, now here's the tricky one. I see 0 times z, okay, is equal to 1. Okay, so that's what that last equation looks like. Now I'm asking, what is the solution set here? Well, there's no solution set because that last equation cannot be satisfied with any, no matter what your choice of x, y, and z are. Okay, because no matter what you put for z here, it's not going to appear, or x or y, nothing will appear on the left. It'll be 0, but the right hand side is 1. So there's no way you can satisfy this last equation. So there's no solution to the system. Okay, no solution. Right? So now you begin to you see how you can recognize from an augmented matrix whether the system is consistent or inconsistent. So this is an inconsistent system. And because it may have arisen from a system of equations that weren't in echelon form, so you couldn't obviously tell whether there's a solution or not, because the echelon form has no solution, the original system has no solution. Okay, so in the last column there for an augmented matrix, if I see a row where that last column in the augmented matrix, the right-hand side column, has a non-zero entry, but everything else to the left is 0, then that tells me the system is inconsistent. So a row like that is identifying an inconsistent system, which is very important to know because we want to know whether a system of equations has a solution or not. All right, so let's move on. So here we have a system of equations, or an augmented system in reduced form. So let's write out the system of equations, and let's identify what the solution set is. So here we go. So I get x1 plus 2x2, okay, plus 2x4 is -3. And then I see in the next equation, I see my x3 minus 5x4 is equal to 8. And then the last equation has all 0, so I won't even write it. Okay, now what I notice here is I have my free variables, so variables that I can choose freely, and I'll just highlight them, not like that, but like this. So my x2 and my x4 are my free variables. So x2 and x4 are free variables. Okay, so just to emphasize that, free variable means they can be chosen freely, but not the other variables. The other variables, x1 and x3, depend on that. So free variables, so I'm going to write down, and this is customary in this book and typically in linear algebra, we give them a different symbol. You don't have to, but let's do that. Maybe sometimes I won't, just to prepare you for the real world. But anyways, let's do it this way. So let's give them a t and an s, okay? Where t and s are any real numbers. Okay, so that's emphasizing that these x2 and x4 can be chosen freely. But x1 and x3 are the leading variables. So let me write that down. x1 and x3 are the leading variables. because they have the leading ones in the coefficient matrix. Okay, so there's my leading ones. You see that? So X1, X3, leading ones correspond to the leading variables. So leading variables. What that means is that they depend on the free variables. So their expression in the solution set depends on your selection of the free variables. So depend on the free variables, as we'll see here in this example. Okay. So I need some more room here. So X1, X3. Okay, so now let's continue on. Let's write out the solution set. So I know there's infinitely many solutions. Okay, so this this tells me right here that there's infinitely many solutions, one for each selection of my variables X2 and X4. Okay, so you know, nobody's going to write out infinitely many solutions. I can write out when there's a unique solution, we just write it out. But often there's infinitely many solutions. How do you write them out? Well, you don't write them out, but you need a way to describe them. And using parameters is the way to do that. Okay, so I'll show you how that works here. So my free parameters, so let's continue them. So my leading variables X1 and X3, they depend on my parameters. So let's rewrite that first and second equation. So I'm going to do that here. So X1 equals, so I'm going to move the two free variables that I see there. Notice the leading variables only occur once in each equation, because through that process of row reduction I was able to eliminate variables, leading variables in all the other rows. Once I've identified a leading variable in one equation, I can use that equation to eliminate that variable in all the other equations. Okay, so a leading variable will only appear in a single equation. Okay, all the other variables that appear in that equation will be the free variables. So here's my first equation. I'm going to put my free variables on the right-hand side, which is customary to denote that this is how the x1 variable depends on those parameters. So I get my -3, and I put the 2x2 on the other side, but I'm going to change it now to t, and I'm going to change my 2x4 into 2s. So 2t minus 2s. Okay, and then my second equation, my leading variable is x3, and I'm going to put my my free variables on the right-hand side, which is 5x4, so I get plus 5s. Okay, so there's my t, there's my s. So this is the solution set written out nicely. Set. Okay. Now I don't have to specify, if I say a t and an s like that, I don't necessarily have to specify it. It's understood that they're parameters, okay, but you may see this written down. Okay, so this form right here in brackets is explicitly describing the solution set, and it's an efficient way to describe the solution set. Namely, you select t and s, and then x1 and x3 are computed this way, and the resulting set of 4 numbers is a solution to the system. So let's just take an example. So for example, let's take t and s to be 1. Okay, so what that means in my solution set is x1 is equal to -3 minus 2 minus 2 equals -7. X2, remember x2 was a free variable, t, and I selected t to be 1, so I'll just write that down. My x3, though, was a leading variable, so it's going to be 8 plus 5, so it's 13 for that selection of s. And then my x4 was the s, which I selected to be 1. So I get this 1 point in the solution set, being -7, 1, 13, and 1. And you can check that this satisfies those equations at the top there. Okay, so 7, 1, and 13, and 1. Okay, that's just one of the infinitely many solutions I have. Okay, so finally, we're getting near the end here. Back substitution. So another example here. Let me isolate the leading ones. So there's my leading ones. So my leading variables x1, x2, x3, and my free variables are going to be sorry, that's not an x3. Let me rewrite that. That's an x4, isn't it? Yeah. So my free variables are going to be x3. Actually, just a single variable. Okay, that's my free variable. All right, so let me do this here. I have my x1, express my leading variable in terms of the free variables. Now, this is a form of back substitution. So this matrix could be worked on a bit more. Okay, but at this stage we can find the solution. Back substitution means start at the bottom and work your way upwards. So the bottom equation is the simpler one, and the bottom one, here we go, is x4 equals 3. So I'm going to write it this way, and I'll just make a note here because once I'm finished you might not see where I started. So I started here at the bottom. Okay, looking at my matrix. So I see that x4 is 3, fine. And then I go upwards and I see the next equation, and the leading variable is x2. So I'm going to write down, I'm going to solve for x2, and I see it's minus 1/2 plus 2t. So I'm going to call my, I'll keep it in the same color here. So x3 be the free variable. I'm going to change its into the parameter t now. Okay, so I'm going to use that now. So looking at the second row there, my second equation, solving for the leading variable x2, is minus 1/2 plus 2 times x3, which I'm now calling t, so 2t, and then plus 3/2 x4. Now x4, I go down to see what it was, and I see it's a 3. So this is the process of back substitution, why I start at the bottom. And now I'll just simplify this. So finally I get an expression for x2 depending only on the free variables. Okay, so I'll put that parenthetically here, x2 depending, because previously, if you look at that second row, the x2 depends also on x4 variable, right? But I've already solved for x4. It's now known to be 3, so x4 doesn't appear in this equation for x2. So x2 only depends on the free variables, not the leading variables. The leading variable 4 there, x4. So x2 depending on free variable. Okay, so that's an expression of x2 in terms of the free variable. Okay, good. Now I can move up to x1. Okay, so let's look at the equation for x1. It starts with a 3 on the right hand side. Then I have 2/7 for x2. Okay, so when I move it to the other side, it's minus 2/7. Now for x2, I've just figured out an expression for it in terms of the free variable. So once again, my aim in this is to express x1 in terms of only the free variables. Okay, so I see an appearance of x2 in my equation for x1. x2 is not a free variable, but I've already solved for x2 in terms of the free variable. So I'm going to use that expression here. So there it is. Okay, so there's my x2. And then I have 3/7. That's my free variable. So I put that on the other side. So 3/7 t. And then I have my leading variable x4. And I'll move that to the right hand side, but I'll express x4 in terms of, well, there's no leading variables for x4. It's just equal to 3. So I get minus 2/7 times 3. Okay, so now I can simplify this. Did I simplify it yet? Not yet. Okay, so that's my, yeah, I can simplify this actually. I did it here, so it just turns out to be, you guys do it, 1 minus t. Okay, so there we go. My leading variables, x1 and x2 and x4, expressed entirely in terms of my free variable, which I'm calling t now. It just turns out that x4 doesn't depend on the free variable, so there's no t there. It's equal to 3. Okay, so that's the process of back substitution. All right, so some more work to do. Let's write out some, I'm going to write out some of these equations because you can check the answer below. So here's an example where we can go from augmented matrix to system. So let me just write out a few of these, because when we get to the answer below, we can come back and check our original equation just to see if our solutions are working out. So let me just write a few of them down. x2 plus 6x3 plus 2x4 equals 2, and then 3x1 plus 6x2 plus 18x3. So this was the original equation system that we had, and then we put it into an augmented matrix form to perform these row operations, plus 12x3 plus 10x4 equals 4. Good. So here we go. Now this is step-by-step reduction. So there's my first leading one. So what I want to do is eliminate those the variable x1 here in all the equations below, which means I want to make these terms down here. Let me put it in yellow. I want to make them 0 by row operation. So I'm going to change, I'm going to add certain multiples of row 1 to these other rows to eliminate these numbers below it to be 0. So this is what you'd end up to be here. Okay, let me just make it here. So I've made those terms 0. Okay, so you can see what we did. I'll just fill in this statement here. What did we do to the second row? We subtract 2 times row 1. All right, and I had to do 2 times row 1 because it's the 2 there, this 2, I want to eliminate. Okay, so if I multiplied that top row by 2, you can see what happens. I'd get 2, 4, 6, 8, 2. Then I subtract that row from the second row. That makes that a 0, and it changes all the other terms into what you see there. For the third row, I had to subtract 3 times row 1. Okay, and for the fourth row, I subtracted 4 times row 1. Okay, so that's, once I've done that, that's the form I get. All right, so now we're going to continue on. So I isolated my first leading variable at the top, and I made zeros all below it. Now I'm going to isolate my second leading variable, which would be this one here. I want to make that one a 1. So I'm just going to write down now what it looks like. So 1, 0, 0, 0, 2, 0, 0, 0. Now the third row, I make that a 1. So I divide the third row by 9. So minus 1/3 and minus 1. And once that's done, so the bottom row I don't have to change yet. So let's leave it like that. But once that's done, I can eliminate this 3 I see up here. Sorry, I should put that in yellow. So this 3 here, I want to eliminate that. So for my, I'm going to subtract 3 times my new row 3. Okay, not the old row 3, but the new row 3 from row 1. So what I would get is, okay, so let me write it down one more time before I do that. So it's 3, 4, 1. Okay, so that's my equivalent matrix, and then let's continue on. So now I'm going to eliminate that 3 in the top there. Okay, so when I do that, I get 0, 5, 4. So I've subtracted 3 times the third row from the fourth. I don't have to do anything to the second row yet. Minus 6, 0. And I don't have to do anything to the third row yet. So there's my slightly simpler equivalent system. And now I want to target this term down here, make that a leading one. Okay, so I go one more step. So 1. Notice I don't have to change the columns as I move from left to right. So the columns won't be changing. And I'm just going to quickly write them down. So now my last row, I'm just going to make that 6 into a 1. So that's the leading one in that row. And then I'm going to use that to eliminate the other terms above it. And you can check that this is what you get. Actually, the second row becomes 0. So 2, 0, 4. Okay. So it's not quite echelon form. I guess I should put the bottom row, the third row now, the second row, sorry. The second row I'm going to put at the bottom. So my new second row is going to be my third row that I see previously, minus 1. So my top row is 1, 2, 0, 0, 4. And I move that there. And then the bottom row and the previous one is going to be my new third row. And then I've moved the second row to the bottom. Okay, fine. So there we go. And then these are my leading ones. 1, 2, 3. And this is my free variable, one free variable here. Okay, so let me write out the solutions now. So x1 is equal to 4 minus 2t. So I'm going to call my free variable x2 t. And then x3 is fixed at minus 1. And x4 is 0. x4 is 0. Okay. So let's just test. So let's take t equals 1. What do we get for a solution for this one. I get 4 minus 2 for x1. I get 1 for x2. 3 is minus, x3 is minus 1, and this is 4. Now I want you to check that this works. So I'm just doing a check on one choice of my solution set. So you can check that this satisfies all 4 of those equations. Okay, so there you go. A lot of stuff here, but you'll soon get used to this because you're going to be doing it all the time, even when we move away from the topic of linear equations. The process of what we call a Gaussian elimination here, this process of putting a matrix into reduced echelon form is going to be used over and over again in this course. Okay, so I'll see you next time when we do section 2.1. So I will finish that now.